Oh, it's been such a long time thinking about capacitors. I don't know. What we're going to do here in this video is we're going to look at capacitors and what happens whenever they are first initially charging, the instant they might be charging, and a long time after they are charging here. So we call these very long times and very short times. So let's take a look at this example. We have a, 12 volt battery here at some EMF, and we hook it up to a capacitor here, okay? And let's say in parallel with this capacitor, we also hook up a light bulb. Whoop. What will the light bulb look like the instant that this is here? We'll even do this. We'll throw a little switch in here. This will make things nice. So here's a little switch. When I close this switch, so this capacitor is uncharged. When I close the switch, what will happen to the light bulb? Immediately when I close the switch, okay? Then, after I've let the switch go for a long time, which we'll say is like an infinite time, what will happen to the light bulb, okay? So this is what we need to know. When we close this switch and complete the circuit, this capacitor is uncharged to begin with. Since the capacitor is uncharged, it is going to take charges here freely. It takes no work to put a charge onto that capacitor. Because of this, at the instant it's turned on, an uncharged capacitor, it will act as a short in the circuit. And what we mean by that is that you won't actually see a capacitor there. What it will look like is just a wire. It'll look like there's nothing there. And because the circuit doesn't see the capacitor yet, all of the current is going to go this direction, all of it. None of it is going to drop down through the light bulb, because why would I go through a resistor? If I've got an easy path to get out, I'm not going to go through a resistor. That's insane. So the instant that this switch is thrown, the capacitor is acting as a short, and the light bulb will be completely dim. It will be essentially off. Now this will only last for an instant, because an instant later we have our first charge here. And as soon as we begin to build up charge on this capacitor, what's going to happen is, okay, some of the current is going to go through here, but a tiny bit of those charges are going to go, wait a second, I don't want to go to that capacitor. It's got some potential now. It's filling up. I want to go somewhere else. And some of that current is going to drop down here. So the light bulb is going to start as off, and then it's going to start to illuminate. Now, when time goes out all the way to infinity, okay, what's going to happen there? Well, at some point, our capacitor is going to be filled up. We can't stuff any more charges onto that capacitor. It is completely filled. And when the capacitor is completely filled, what is going to happen is the current is going to come around and go, okay, well, I can't get through the capacitor anymore. It's completely filled. I can't put anything there. So at time equals infinity or approaches infinity, we actually look at a capacitor that has been fully charged. We look at it as a break in the circuit. And if you have a break in the circuit here, well, you can't have a current run across that, so all of the current is going to come underneath through our light bulb. So at time approaches infinity, the capacitor is going to act as a break in the circuit, okay? You're going to get no current in this scenario compared to initially where you had all of the current. Okay, so that's what's happening for a short time and a long time for capacitor. When we say short, we mean the instant that capacitor is starting to accept charge. It is an uncharged capacitor that is doing that. So it's starting uncharged here, and then we are charging it up. When the capacitor is fully charged, which we can normally think about that as at time infinity, it's a break. Now the reason why we call it like time equals infinity, and if you checked out the RC derivation video, what you might notice is that when a capacitor is charging, so this is some Q and this is some T, a capacitor isn't just charging as a linear function. A capacitor is actually charging with an exponential curve to it. It's actually charging as the equation Q of T equals the max charge of the capacitor times 1 minus e to the negative T over RC, where that RC is the tau, the time constant. And that means that this capacitor is actually going to charge like this, where this right here is some max charge that we're going to level out at. So we never actually get to that point, okay? We never actually get to this point Q. We just come very, very close to it, even at time infinity. So what we just generally say here is, yeah, at time infinity we are fully charged, and that's the case there. Same thing the other way, when we discharge a capacitor, we kind of go down like this. We never completely discharge a capacitor, but we become arbitrarily close at a long time for discharging, okay? So those are just some things to keep in mind. Properties of capacitors: whenever you're uncharged and you begin to charge them, when they're fully charged, they act as brakes, and kind of what we're looking at here in terms of graphs at that point, okay? So hopefully that makes some sense for you. Hopefully as questions pop up about this, you'll get more ideas of what's going on. And remember that brightness is dependent on power, and that is dependent on current there. So that current really matters in what's going on there. Okay, so that's that for capacitors. We are finished here. Y'all take it easy. Adios.